All right, this is section 14.3, part D, and we're now going to turn from the FTC for circulation or work integrals to trying to develop an FTC for our flux integrals, the f dot n ds's. We're going to have to start with our test again. We had said that the FTC applied for the work or circulation integrals when we had a conservative vector field. It turns out that the condition we're going to need for the flux integrals is we're going to need what's called a source-free vector field. A vector field is called source-free if there exists what's called a stream function, phi, such that f is d phi dy and g is minus d phi dx. Notice the swapping here of the variables and the negative on the second one, very reminiscent of what we did when we did those normal vectors from the r primes before, and that certainly is not a coincidence. All right, here's our test. F is going to be source-free if, and I'll write the abbreviated form, f sub x is equal to minus g sub y. Quick note, we're only going to do these for now for two-dimensional functions, just like we only did the flux integrals for two-dimensional functions. All right, so we're going to verify in example 5 that this is a source-free vector field, and then we'll find that stream function phi. So first of all, the test. F sub x has to equal minus g sub y. Here's my f and my g. So f sub x is 2x. That has to equal minus, and g sub y is negative 2x. And of course that's true. So our vector field F is source-free. Again, what exactly source-free means, we'll talk a little bit more about that a little bit later on, but it does have a very physics interpretation. All right, I want to find the stream function. So I'm going to go back up to here. d phi dy is equal to F. So in this case, d phi dy is equal to x squared. And same process we're used to now. Phi is going to be x squared times y, plus a constant that could depend on x. We also know that, and I'm just going to bring the negative to the other side, d phi dx would be minus g. So in this problem, d phi dx would be minus a negative 2xy, or just a positive 2xy. And integrating that one, phi turns out to be integral of 2x would be x squared times the constant y, plus a constant that could depend on y. So my stream function phi definitely includes the x squared y. That was part of both versions. And then it looks like there's nothing else. So I think the c of x and c of y this time are both zeros. And there's my stream function. All right, so we won't do a ton of examples of that because it's so similar to what you were doing when you were finding potential functions. The test is different, and you simply have to use a slightly different setup. It's not the gradient anymore, but other than that, we're looking at the same process. So here is the FTC for flux integrals. It requires that F is source-free. You cannot use this unless you have a source-free vector field. If the stream function is phi, like we just found, then the flux integral, f dot n ds, is phi of b minus phi of a and b being the endpoints of C again. This means we can draw very similar conclusions to the conclusions we drew with the circulation form. We can say that, again, if f is source-free, this only applies if f is source-free, Then, first of all, the flux integral will be path independent. And secondly, the flux is equal to 0 for any closed path C. Again, the idea on a closed path being B and A are the same, so the right-hand side of that equation just becomes 0. All right, example 6. I've given us a vector field, and as a matter of fact, it's the exact same vector field that we've already found our phi for. In this last example, we showed that it was source-free, and we found phi. So I'm using that same f, which is source-free, and had a phi of x squared y from example 5. And this time I'd like to evaluate the flux integral, f dot n ds, two different ways on the line segment from 4, 0 to negative 2, 2. So we'll go ahead and we will use the FTC as one of our two methods, and then we'll also go back and use the old method, the parameterization method. Once again, my goal here is just to show that we get the same result and kind of, at least for one example, verify this FTC. So since I've got it started here, let's go ahead and use this and do the FTC as our method 1 this time. We know, since it's source-free and we have the stream function, that the flux is just phi of B minus phi of A. B, the ending point, was negative 2, 2. And A, the initial point, was 4, 0. So plugging into my phi function, I would have negative 2 squared times 2, subtract 4 squared times 0, which is going to give me 8, minus 0 is still 8. All right, for method 2, let's hopefully get that same answer going back to our old way, the parameterization method. In this case, we actually have to parameterize our line segment. So I'm going from 4, 0 to negative 2, 2. By the way, you can certainly look at that and discover the equation y equals mx plus b that way, or you can also use the direction vector method like we do in the three-dimensional case. Works just the same. Maybe I'll use that method this time since it's a little less obvious what the y-intercept is. If I would like to parameterize this, I could say that my direction vector v is terminal minus initial, so negative 2 minus 4 would be negative 6. 2 minus 0 is 2. My vector OP, I'll use 4, 0, the starting point. And R is just t times the direction vector plus the point. Or negative 6t plus 4, comma 2t plus 0. One advantage of doing it that way is that way my t values automatically go from 0 to 1. I don't have to worry about it. All right, I'll need r prime, negative 6, 2. And then because this is a flux integral, I need n. And this will be small n. It's not going to be the unit normal. So I'm going to take the second component and bring it up and make it the first component. And then that negative 6, I got to turn that into a positive 6. And that makes it the outward normal. And then my flux integral is the integral from 0 to 1. Oh, and I did it again. I forgot to put my f in here. F is x squared. And remember, let's see, here's r. So this is x and this is y. So x squared, negative 6t plus 4 squared, comma negative 2 times x times y, which is 2t. I always run out of space on this end. Let's see, there we go. And you can't see that at all. Tell you what, let me rewrite that. I'll do a little bit of algebra and rewrite. It was negative 6t plus 4 squared. And then that's really a negative 4t right there. I'm going to distribute that in and make that a 24t minus negative 24t squared and make that a negative 16t. So again, I was taking the negative 4t times the negative 6t, that's 24t squared, and then the negative 4t times 4 to give me the negative 16t. There, now I've got it written so you can actually see it. All right. To get my flux then, the integral from 0 to 1 of f dot n. So I'll have 2 times that negative 6t plus 4 squared plus 6 times the 24t squared minus 16t from 0 to 1, and that's not too bad. We can type it in the calculator exactly that way. And I did that, and what did I end up with? I ended up with 8, thank goodness, because that's definitely what I was expecting from method 1. All right, so there's the 2 different methods giving us the same solution. FTC coming up with the same solution as the original method for finding a flux integral. All right, let's try another example here. In example 7, my goal is to find the flux for f being y comma minus x, and I've got several different paths. Actually, 2 different paths, I guess. Path A is the unit square with vertices given, and path B is the top half of the unit circle from 1, 0 to 0, 1. Since I'm using the same vector field, 2 different paths, it would really help me if I could determine whether this was source-free, so I don't have to parameterize 4 different sides of that square and then parameterize again for my half unit circle. I could just use the FTC. So it's probably worth it to check and see if indeed my vector field is source-free. So let's check. Is f source-free? Well, let's see. The test for source-free, f sub x equals minus g sub y. Here's f, here's g. And f sub x is 0. G sub y is also 0. So yes, we definitely have a source-free vector field. And then I need to write out my phi, I guess, equations. Partial derivative of phi with respect to y must equal f, which is y. So it looks like phi is going to be 1/2 y squared plus a constant that could depend on x. And the partial derivative of phi with respect to x must equal minus g. Again, those are just 2 kind of given equations that we use every time. We don't have the gradient this time, so we use those. minus g would actually just be a positive x. So this one gives me phi is equal to 1/2 x squared, plus a constant that could depend on y. And comparing these, I'm going to say that the stream function phi, the 1/2 x squared goes with the c of x, and the 1/2 y squared goes with the c of y. So I just have 1/2 x squared plus y squared. All right, so for part A, I wanted to find the flux over the unit square. Zero, 0, 1, 0, 1, 1, and 0, 1. And again, we'll assume we're going around counterclockwise since I didn't specify anything else. Well, this one's great because we clearly have a closed path. And since I have a source-free vector field on a closed path, that tells me the flux is 0. By the way, this is a good time to talk about that kind of meaning behind the word source-free. Flux, remember, is how much of your vector field crosses the boundary of your C. And what this is saying is that the net amount that crosses this boundary is nothing. If I had a source of material in here, I would have to have a net flux that's positive. The source would cause my material to move out across the boundary. If I had a sink, if my material was flowing into a drain in here, I'd have a net flux inward, or a negative flux. Because the flux is 0, there's no source and no sink. And that's where the word source-free actually comes from. All right, part B, same vector field. So I already know it's source-free, and I already know what phi looks like. C this time is the top half of the unit circle. From 1, 0 to 0, 1. And since I've already done all the work, I'll just use the FTC to say that would be phi of the ending point minus phi of the starting point. So 1/2, here's my phi, plug it in. 0 squared plus 1 squared minus 1/2 1 squared plus 0 squared. And that one's actually going to give me 0 as well. Now this wasn't a closed path, so the fact that that was 0 was a little bit more serendipitous, but we did get 0 once we used that FTC. All right, that brings us to the end of section 14.3.